Okay, so now we're looking at an example, our real estate example, okay? And what we always start with is a summary statistics, okay? So this is the function we use to get summary statistics, and we want summary statistics for price and square meter, those two variables, okay? And what we see here is that the number of observations is 30, right? And so this means that we have 30 data points with the price and the size of each apartment. And what we have here is the mean of the variables, and you should always try to find out what they mean. Okay, so for example, the average price is 8.78, which is measured in millions of kroners. So the average apartment price is 8.78 million kroners in our data set, okay, in our sample. And these range from 3.71 million kroners to 15.7 million kroners, right? And the standard deviation says something about the distribution of our data set. So in the case this is normally distributed, then you can say something about the probability that a certain price would lie within 3.43 around the mean, okay? And likewise, the average size is 89 square meters large, has quite a large standard deviation, and of 32 square meters. And the range of our data is from 40 square meters to 151 square meters, okay? And what you also want to do is in addition to the summarize function, you want to use the correlate function, because then you can find the correlation. This is the correlation between the price and size. Between the price and size. And we see that the correlation is 0.911. The correlation is always between -1 and +1. And we see that the correlation is greater than 0, which means that the slope is greater than 0, okay? Which means that our graph will look something like this, okay? With price and size, okay? So we know already that our graph is upward sloping. So what can we do to find the fitted OLS line? Okay, so what is the OLS regression line for relating apartment prices to the apartment size in square meters? Well, we can use some equations, and which we went through in the last video, and that is we find the slope first, and this is just the correlation times the sample standard deviation for y, and the sample standard deviation for x, okay, that ratio. And this is for the price, and this would be for the size in square meters, okay? So if we just plug in the numbers, we remember that the correlation was 0.911. We found that from here, okay, the correlation, and then we need the sample standard deviation for price, and the standard deviation for price is here 3.438 times 3.438 divided by the standard deviation for size, and that would be 32.37. okay, 32.37. okay, so this means that we get a slope of 0.0968. okay, so that's how we find the slope, and we can now find the intercept. It's just the y bar, the average price, minus the slope times the average size. Okay, and we have the average average price of 8.782 million kroners minus B1, the slope is 0.0968 times X bar, which is the average size. And the average size is 89.433. 89.43. Okay. Let's see. And that would give us a B naught of 0.124, right? So that's our B naught. So our equation is really price, or our y hat, our estimated y is the estimated price is equal to the intercept 0.124 plus 0.0968, because this is the slope, times the size. Okay, and that would be in square meters, right? So here we have million kroners equals million kroners, right? The intercept has to be the same denomination as the y variable, right? Otherwise you can't add stuff. So you can't add apples and pears, right? Or kroners and square meters. Plus the slope is denominated in million kroners per square meter, right? So this is million kroners per square meter times the size is measured in square meters. And you see that the square meters, they cancel, right? So you're left with million kroners, which is correct. So now we tested that our denomination is correct. Okay, so of course you don't have to do this by hand, even though it's quite nice to know because of the understanding. But you get Stada to do this for you, and then you use the function of regress, the regress function, and you regress price on square meters, and Stata gives you a lot of output, right? So, for example, you have the number of observations, and you also get the coefficients, okay, which are B0 and B1, right? The intercept and the slope. So the slope is actually here by the square meters, and that's slope, and this would then be the constant, or as we say, intercept, and this price, it's the y, okay, y variable, okay, and the square meters would be the x variable, okay. So here you actually get all information which you need in one go, okay. So let's see, yeah. And one other thing is here you have the r squared, right? And this is from r squared, and this is the correlation between x and y squared, right? So what you see is that this equals 0.911 squared, and why 0.911? It's because this is the correlation between x and y. So if you plot this in, you could actually look at what your r squared becomes before you even run the regression, okay? And what is r squared? It's actually the portion of the variation in y, which is explained by x, okay, as compared to the normal model. We'll look into that later, but this is how you can get r squared in a quick manner. And the root MSE, this is just the standard error, sample standard error of the errors themselves. Okay. It's really the standard deviation of residuals. So then you can actually, if you get y hat from the equation, then you can actually calculate the estimated y hat, the estimated price, and in addition you can create a band around it, okay, because you know the distribution of it. So here you can see that the standard deviation of the error is 1.44 million kroners. Okay, we'll get into that later. So how do we interpret the fitted line? Okay, so what we do is that we make a two-way graph. It's of type scatter with price and square meters, okay, but we band these together because then we can put in some other parameters and make one graph on top of the other, okay. So here we get a scatter plot, and here we get a line, okay? And LFIT stands for linear fit, which is by type of OLS, okay? The fastest way to graph an OLS line in Stata. And this line gives you y hat, the estimated price, and this scatter gives you these points, right? And here you see that you have some errors, right? Some errors. And you know the standard deviation of these errors away from the line is this 1.44 million kroners, right? Okay, so now you have a line which gives you an estimated or an estimation of the price of an apartment of any size, okay? So if you would want the size of 110 square meter apartment, you could easily find that by either looking at the graph here and get around 11 million maybe, or you could just plot 110 into the equation. For example, let's see, y hat would be 0.124 times 0.911. No, that was not that was the correlation. The intercept was 0.967 or 968, 0.968 times 110, okay? and you would get a result, okay, around 11 million. And so you can see the residuals that these are the scatter plot actually gives you the true values, okay? But as you see, even if you have a true value above the line, then if you move slightly away from that size, then you get a totally different estimate, okay? And why are the errors so different based on a small difference in size? Well, it may be because this specific apartment, for example, had a balcony or an extra car space, or has a better view or whatever. So these are factors which we have not included in our model. And in the next lecture, lecture 6, we are going to look at how to include these or more factors into our equation to get an even better fit. Okay? So, what can we say about the intercept? We can look at this and just out from the denomination of the intercept, it's in million kroners, right? And one thing you can do, there are two things you can, or two ways you can interpret the intercept. One is to say that the intercept is the portion of y that is present for all values of x, okay? And what you can think of is that if you have x on the x-axis and y on the y-axis, and you have an intercept here, b0, and you have a line here, then this b0 is present for all the data points you have. For example, for all apartments. So, for example, for an apartment, what kind of common factor do you have? For example, if we look at the real estate example, how do we interpret the intercept? Well, we could interpret it as 0.127 kroners is the value of all things in the apartment which is not dependent on size. And this could be, for example, the right to live, okay? Because everybody has to sleep somewhere, and an apartment is quite practical. Or it could be like view, or it could be quality of neighborhood. Okay, and that's one way of looking at the intercept. A second way to look at the intercept, which is not relevant to our example, it's sorry. The intercept estimates the average y when x equals 0. Okay, so for example, if x can be 0, then in a logical sense, then the intercept would be, for example, the price or the value of y given x equals 0. In our example, if the size of the apartment is 0, then probably you would not pay 0.127 million kroners for it. 127,000 kroners for nothing. Okay, so in the case that x equals 0 is a logical value, then the intercept can tell you something about the y value. And we have talked about the importance that the intercept has the same units as y, okay? Because million Norwegian kroners should be equal to million Norwegian kroners, right? And we can also look at case, which is extrapolation. And let's see if we are, yeah. And for example, in some cases, we should be careful extrapolating. Okay, we remember that our data contain data of apartment sizes from 40 square meters to 151 square meters, and which is here about, so from here to here in this interval, from 40 to 151, and if you extrapolate, for example, down here, then you are actually assuming that this linear relationship between x and y continues also outside of the range of your data. But you can't really say that without gathering more data from this segment, right? Because it could be such that this relationship goes in either direction, right? Because, for example, in the example we have, you would not want to pay money for an apartment with 0 square meters, right? So you have to be very cautious when you interpret an extrapolation. Okay. We could also interpret the slope, right? Here, slope. And this is in million kroners per square meters, right? And this is really the predicted change in y if x changes in by 1 unit, right? So if you look at 2 different apartments, and one apartment is 1 square meter larger than the other, then your estimated value increases by this slope. So for example, if you have a 1 square meter increase in the apartment size, is predicted to increase price by 0.097, and if we include the denomination, we have million kroners per square meter times 1 additional square meter. These cancel out, so you're left with 0.097 million kroners, right? Okay. What if the change is something else than just 1? Then to find the effects of changes other than 1 unit, then we just multiply the slope with the number of units. So for example, a 5 square meter increase in the apartment size, then we take 0.097 times 5 as measured in million kroners, should be equal to, let's see, 4, 5, 3, 5 equals 0.485 million kroners, right? So now we have found how much more an apartment would cost on average if it had 5 additional square meters. Okay, and a word of caution is it's not correct to describe the slope as the change in y caused by changing x, because really you can't change x based on on the data. Okay, so for example, if you have an apartment, you can't just add 5 square meters to your apartment. That would often be quite difficult. And this regression doesn't give you a causality, okay? Because if you regress x on y, would give you basically the same r squared as y on x. So what is causing what? Is it the extra square meters causing a higher price, or is it a higher price causing extra meters? Okay, so yeah, so in some models, the causality is quite difficult to interpret. Okay, maybe not so much here, but okay. See you next time.